Okay, guys, good morning. We're going to do some science today. We're going to continue. We did heat and energy. This one is going to be on sound and waves. So we're going to go up to the top here and just read about mechanical waves. So this says waves are everywhere. We encounter them every day. We see light waves, hear sound waves, use microwaves, and maybe even do the wave in a football stadium. Even waving hello to someone is a wave-like motion. In the ocean or lake, water ripples and waves. Those waves are caused by some disturbance, such as a rock dropped in the water, a moving boat, or a larger movement deep at sea. Simply put, a wave is a disturbance that transfers energy. Waves do not transfer matter, but may travel through it. The matter a wave travels through to transport energy is called a medium. A medium can be a solid, that can be a liquid or a gas. The wave travels through the medium and displaces matter temporarily, but the wave has passed, the matter returns to its real position. Waves that transfer energy through matter are called mechanical waves. So, when a boat goes through the water, you guys, there's like a little wake, but eventually the lake gets calm again. So eventually things return to normal. This says mechanical waves can also be transverse or compressional, also called longitudinal. A transverse wave moves matters perpendicular to the direction of the wave. One example of a transfer wave is a water wave. The wave travels forward through water but displaces water either up or down. And this diagram kind of shows that. The wave travels forward through the water but displaces the water either up or down. A wave is on a string. It also traverses earthquakes or S waves. So you can see here it's kind of going up and down, okay? And that'd be a transverse wave. It's kind of up or down. The transverse wave has high points called crests. So you can see up here that'd be a crest, and low points called troughs. That would be down here. The line exact between the highs and lows represents the rest position. So this would be the lake right here if no boats were going through it or no one was throwing any rocks. But if a boat goes through it, the water's going to go up, it's going to go down, okay? But then, like I said, it returns to the rest position. Crests and troughs represent the displacement particles the mechanical wave travels through. The distance from the rest position to the crest or from the rest to trough is called an amplitude. So that would be up here is the amplitude from the rest position to the high point and the rest position to the low point. And that is called the amplitude. Waves carrying more energy have higher amplitudes. A water wave with a high amplitude will be taller. The distance from the one crest to the next is called the wavelength. So if a bigger boat comes through, obviously going to make bigger waves. Smaller boat, maybe not as much. Okay. So the next one we're going to do is it says a compressional wave. And this plays matters the same direction the wave is traveling. Sound waves, an oscillating spring, and earthquake P waves are compressional. Sound travels particles of air, pushed forward, and then pushed back the original position. So this one kind of goes left and right, and the other one goes up and down. So transverse goes up and down. Compressional kind of goes side to side. And you can kind of see this here. This one goes side to side. This is like maybe even like a slinky or something. If you pull it out and bring it back, it's going side to side. So in a compressional wave, the movement of particles cause high density in some areas and low density in the others. In the high density area called the compression, the particles are closer together. In the low density area called the rarefaction, the particles are spread out. Waves that carry more energy have more dense compression. The amplitude of compressional wave represents the density of the compressions. The sound waves with a bigger amplitude will be louder because the vibrations in the air and eardrum are larger. The wavelength of compressional wave is the distance from the beginning of one compression to the beginning of the next compression. Fill out the T-chart with reading from the past. So this is going to ask you about a transverse wave and a longitudinal wave. So if you go up right here, this calls a transverse or compressional wave, also called a longitudinal. So these three are all the same. So you're just going to read about, this one's mostly up and down, and you can fill in some of the information on the one side over here. So this would be The transverse wave is going to be kind of the one in the water we talked about. And then the compressional one is more the longitudinal or the spring. It goes side to side. So compressional or longitude side to side, transverse is up and down. So you could just look in this reading right here for the longitudinal wave, and the transverse is about the water. And then you just kind of fill in the definition, example, and the parts, okay? And it says both light and sound travel in waves. Use the terms of the word box to label the part of the waves here. So if you go up to right here, you can see there's amplitude, there's crest, there's trow, and then the wavelength. So you're just going to basically take the information from this chart right here and put it into this one right here. And all the terms are just right there, okay? And equilibrium would be basically, that's the calm. That's when everything is, when there's nothing in the lake and everything is calm, okay? And this is the sound wave. This is the one that goes side to side. And what you're going to do is you're just going to basically use this diagram to fill in that one. And this one is kind of like the slinky that I mentioned. And this goes side to side. And everything you need to know is just in this one right here. So if you just kind of read through this one right here, you'll be able to answer the second part down here. That's a sound wave. Okay. And this last one is how you figure out wave velocity. So velocity is a wavelength times a frequency. Okay. So this one would be 3.4 is the wavelength, and the frequency is 2.5. So it's just going to be 3.4 times 2.5. This one would be 280. The hertz right here is the frequency, and the wavelength is the length of the distance. So it's just going to be 1.5 times 280. This one's 3.4 times 2.5. This one would be 135 times 5.7, and this one is 220 times 4.2. Okay, so that's a formula for velocity. It's equals wavelength times frequency. Okay, and here are the answers down here. So here's the there's going to be a transverse wave and a longitudinal wave, and here are the answers to these questions up here. So you've got 1 through 10 there, and this one is 1 through 10 there, okay? So if you're having a hard time, you can go down and look, and here are the answers to the basic math problem we just did, okay? So hopefully that helps you guys. Some of the stuff will be probably on the science test, and this is just basically about, you know, waves, energy, sound. So go ahead and just read through these. If you get stuck, like I said, you can go down to the bottom and the answers are right there. Okay, hope everyone has a nice day. I'm going to start reading here in a little bit. So hopefully I'll see some of you guys soon. Bye.